Okay, so we're going to kind of back up a little bit. We've been talking, in the last unit about bore models. We did the basic bore models. Kind of where did that idea come from? Try and illuminate that a little bit. But basically, something that happened before Bohr came out with his model was that scientists were looking at, they were taking, substances, gases. They were applying a lot of energy to them, a high voltage, run a current through them, excite them, and it'd create these, glowing glass rods, which then if they use, a spectroscope or, if they could kind of, bend that light, kind of like, a prism bends, white light, and see all these colors of the rainbow. If they did that for the light produced from specific elements, that they found that when they separate that light, they found what we call this, emission spectrum, and it's kind of hard to see up here, but basically that there was a lot of darkness and only a few specific lines or colors. And we can actually recreate that pretty easily. I mean, I got a same apparatus here, that if I turn this on, if you run that and give that energy into that hydrogen gas in a tube there, that you get this pink glow, this pink purple glow. And then if you look at it using a spectroscope or these glass, something that can kind of bend that light, you can actually see those lines. You can see where there's patches of darkness, separation. There's no light or in that range, and then there's bands where there are. And so when scientists observed this, once again, this is before the Bohr model, they observed it and they're like, why does it do that? That's weird. That's strange that you only see these, and they did it for not just hydrogen, but other things too, and they'd get these weird bands of just these specific colors. And so it was strange. But what was proposed basically, going back to our little chart here, that when you have all these colors and all this electromagnetic radiation, every location upon this, even in our visible range, has a specific quantitative wavelength, frequency, energy value associated with it. Every color, is not just a qualitative thing, it's a quantitative thing. That there's a number, an energy level associated with the color of light that we see. And so when they're doing this emission spectrum, that they're looking at all these different elements and all these different colors, each color, each band, right here is just kind of pulled out, but each of those colors represents a specific energy value. That's not a continuous spectrum, that's a line spectrum where there's just specific values, specific energy values correlating with a specific color. And so why was that so big? Well, basically, what was going on is that if you give an electron energy, it can increase its energy level. That'll increase its distance from the nucleus, or, we're kind of, like I said, working reverse engineering how they came out with the Bohr model. But if you give an electron energy from that electromagnetic radiation or other sources, it'll go to another higher level. And the opposite was true, that if you have an electron at an excited state at a high energy level, all right, that if it dropped to a different energy level, because that's what those rings that we know now in the Bohr model represent energy levels, depending on how far it dropped, depending on the jump that electron made down, whenever it drops down, it was releasing energy in the form of light. And so depending on the specifics of that gap, that energy gap of going from one ring to another, that was going to give off a specific amount of energy, which is going to have a specific color. And so basically they looked at these colors and then they lined up, okay, this color is this much energy, and so, okay, the electron must be at these positions. And that's kind of where he ended up with the Bohr model. But it turns out that the Bohr model, it's basically theorizing that these electrons are in orbit around the atom as particles, but it really didn't it worked nice for hydrogen, but it got really complicated and wasn't a very good fit or an explanation for the other atoms. It got kind of out of hand. Schrodinger came along, started talking about, you know, electrons acting as waves, which ended up fitting a lot better and making a lot more sense. Which ultimately, you know, when we start talking about orbitals, which are, you know, three-dimensional spaces where electrons are probably at, you know, where we calculate, okay, there's probably there, and it goes hand in hand with the very famous Heisenberg uncertainty principle. That's impossible to know the speed and location of an electron at the same time. We'll talk about, you know, I mentioned Schrodinger back here, you know, that we'll talk about, you know, the thought experiment that was Schrodinger's cat. It's a very famous, you know, topic. It wasn't an actual experiment, but something he kind of just thought theoretically, you know, what are we talking about? And like we saw, or we'll see in those videos, those other videos, tiny things like electrons behave extremely weird, and you can't measure exactly what's going on the same way we can in the real world. You know, like if I toss a tennis ball, like you can see where it's going, you can predict everything, it's fine. But electrons are so small that, you know, even the act of looking at it, observing it, can change outcomes and you know, collapse possible events from, you know, of happening. It gets really weird. We'll talk more about it in class. But yeah, you know, that's kind of how we got to the Bohr model. But, you know, as we go forward, you know, it really wasn't that good of a model in the end, and we'll kind of get to what's an improvement on that. That's kind of what we'll get into next.